Hello everybody, I want to introduce myself. My full name is Sylvia Delfi Mardiana Putri and my name is 2103408. Okay, I'm here to explain about Newton's laws of motion. Newton's laws of motion. Newton's laws of motion are laws of physics that explain the displacement of an object as a result of the relationship between the value and distance of the force acting on the object. Newton's laws of motion are one of the three laws of physics that form the basis of classical mechanics. This law describes the relationship between the force acting on the object and the motion it causes. This law has been written in different languages for almost 3 countries and can be summarized as follows. 1. First law. Every object will have a constant velocity, and thus there is non-zero resultant force acting on the object. Means that if the resultant force is zero, then the center of mass of an object remains at rest or moves at a constant speed, not accelerating. This is true when viewed from an inertial frame or reference. Second law. An object with mass and experiencing a resultant force F will experience an acceleration which is the same direction as the direction of the force, and whose magnitude is directly proportional to F and inversely proportional to m. It can also be interpreted the resultance for acting on an object is equal to derivative of the object's linear momentum with respect to time. Third law. The action and reaction force of two objects have the same magnitude in the reference direction in the same line. This means that if here is object A, then exert a force of F on object B. Then object B will exert a force of negative F on object A. F and negative F have the same magnitude but different direction. This law is also known as the law of action-reaction, where F is called the action and negative F is the reaction. These three laws of motion were first summarized by Isaac Newton in his Philosophiae Naturalis Principia Mathematica, first published on 5 July 1687. Newton used his work to explain and study the motion of various physical bodies and systems. For example, in volume 3 of the manuscript, Newton showed that by combining his laws of motion with the general law of gravitation, he could explain Kepler's law of planetary motion. Newton's law is applied to objects that are considered as particles in the evaluation of the motion. For example, the length of the object is ignored because the calculated object can be considered small relative to the distance traveled. Change in shape, deformation, and rotation of an object are also not taken into account in the analysis. So, a planet can be considered as a point or particle to be analyzed for its orbital motion around a star. In its original form, Newton's laws of motion are not sufficient to calculate the motion of a deformed object, not solid object. Leonard Euler in 1750 introduced a generalization of Newton's law of motion for solid bodies called Euler's law of motion, which its development can also be used for non-solid bodies. If every object can be represented as a set of the distinct particles and its particles obey Newton's law of motion, then Euler's law can be derived from Newton's laws. Euler's law can be considered as an axiom in explaining the motion of objects the half dimension. When velocity approaches the speed of light, the effects of special relativity must be taken into account. The importance of Newton's laws and their range of validity. Newton's laws have been verified by more than 200 years of experience and observation, and they are excellent approximation to calculation at the scale and speed experienced by everyday people. Newton's laws of motion and general law of gravitation and calculus for the first time can facilitate quantitative explanation of various physical phenomena. These three laws are also a good approximation for macroscopic objects in everyday conditions. However, Newton's law combined with the general law of gravitation and classical electrodynamics is inappropriate for us under certain conditions, especially at very small scales, very high velocities. In special relativity, the Lorentz factor, Earth's mass, and velocity must be taken into account in the formulation of momentum, or a very strong gravitational field. Thus, these laws cannot be used to explain phenomena such as electrical conduction in a semiconductor, optical properties of a material, force in GPS relativistically, and friction system superconductivity. The explanation of these phenomena requires more complex theoretical physics, including general relativity and quantum field theory. Okay, that's all. Thank you for attention. See you. Bye bye.